Greetings, gang, and welcome back to Chapter 6 and Momentum. So what is momentum? Now we probably have some kind of intuitive or qualitative kind of idea of what momentum is. If you start running, you say you're gaining momentum. But let me ask you a couple of questions to see if we can hash this out just a little bit. If you're going to compare the momentum of a guy on a skateboard going 5 miles per hour or a girl in a truck going 5 miles per hour, which one has more momentum? The girl in the truck, right? Why? Well, because the truck has a lot more mass than the person on the skateboard, right? What about if you have two identical twins on skateboards? One is moving at 5 miles per hour and one is moving at 10 miles per hour. Which one has more momentum? The one moving 10 miles per hour, right? Because velocity is also a component to momentum. And indeed, we generally say the standard definition of momentum is its mass times velocity. Now, first things first, is momentum a vector? Well, yes, velocity is a vector, right? So momentum also has to be a vector. That means that momentum not only has magnitude, mass times velocity, but it also has direction, because velocity has to have direction, right? If something is moving with a certain amount of momentum, what can you do to change the object's momentum? Apply a force, maybe? Well, let's figure out what the units of momentum are, right? Okay, we got mass times velocity. The unit of mass is the kilogram. The SI unit for velocity is meters per second. So, the SI unit for momentum is kilograms times meters per second. What's the unit of force again? Well, if you remember, force equals mass times acceleration, so the unit mass is kilograms, the unit for acceleration is meters per second squared. So we got kilograms times meters per second for momentum, we got kilograms times meters per second squared for force. So what would happen if we multiplied force times time? Well, we got force, which is kilograms times meters per second squared, times time, which is seconds, right? That means this is going to cancel with this, and we're going to end up with kilograms times meters per second. That's our momentum unit, right? That's what we're looking for. So if we applied a force over a time interval, right? We apply a force over a certain amount of time, we can change an object's momentum. Makes a lot of sense, right? As a matter of fact, the way that Newton originally wrote his second law of motion looks something like this. He didn't say F equals ma, he said F equals mass times change in velocity over change in time. Crazy, right? At any rate, we call a force applied over a time interval an impulse. This term here, force times time, we call this impulse. And an impulse gives a change in momentum. Usually we say something like F delta t is equal to m delta v, something like that. This, of course, only works, obviously, if the mass of the object is not changing, right? Just the velocity. Now, if an impulse is applied over a very short amount of time, the average force applied during the time interval is much greater. And then if the interval is applied, or the force is applied over a much longer time interval, the average force is much lower, right? So if you want to think of it this way, you can change something's momentum by adding a big force over a very small amount of time, or a small force over a very large amount of time. right? And that's why if you take an egg and you drop it over some padding, generally it won't break so easy. But if you drop it straight onto the floor, right, you know, assuming you have concrete or whatever under your carpet, or maybe you have tiles, something along those lines, if it's rigid, then the egg is just going to shatter, right? Why? Well, the egg, when it hits the floor, is going to have to stop, right? It's going to have to stop all of the egg's momentum. And if it's rigid, right, if it doesn't bend or compress, then the time interval that the floor is going to exert a force on the egg to make it stop is going to be very small. However, if you drop an egg into some padding or something along those lines, then it's going to take a much longer amount of time, because the padding is going to compress as the egg hits it, right? It may even bounce. And at that point, the time interval is going to be much greater, so the force is going to be much smaller. Makes a lot of sense, right? Now, I've included on today's lecture page a link to an egg drop experiment demonstration video. And that should have some of the same physics in it as we just discussed, with much better visuals. And unfortunately, I can't really go around dropping a bunch of eggs on stuff, you know, in my house. So this will do us much better. Now, it is also possible, if you wanted to apply a force over a very small amount of time, to make the force, the actual magnitude of the force, increase by a lot, right? And the classic example of that is breaking a board. Now, if you have some kind of board that you could, you know, put your whole body weight on without breaking it, it's got a structural integrity greater than your body weight. But if you punch it and it breaks, that doesn't mean that you punch greater than your body weight. That's impossible, right? That's crazy talk, unless you're Bruce Lee or something, right? And so instead, instead of being able to punch greater than your own body weight, you punch with probably, you know, a certain amount of force, and you apply that over a very small time interval by punching quickly, right? If you snap the punch over a very small time interval, you can break a board. And I've included a demonstration video for board breaking as well. Please take the time now, go ahead and pause this video and have a look. Now, if an object bounces off of a surface with its original momentum in the opposite direction, how much did its momentum change? So, let's say we have some object with mass m and velocity v, and here's a wall. Eventually, it collides with the wall, and then it starts to move away with velocity v in the opposite direction, right? So how much did its momentum change? Well, that'll be its final momentum minus its initial momentum, right? We've got m times minus v minus m times v. So, minus minus, we've got minus 2 mv, right? So we have some initial momentum, right? And that has to stop, so it has to remove all of this m times v from the equation, and then to make it go backwards, it has to add another m times v in the opposite direction. And so, for an object to reverse its momentum completely, it has to change its momentum double its original momentum. Pretty straightforward, right? Now the important part. And if there's indeed anything you should learn from this course, it is this: that there are symmetries in nature, and from these symmetries arise conservation laws. There are several conservation laws, things like the law of conservation of matter, for example. The law of conservation of matter states that basically the amount of matter in the universe stays the same, more or less. You might burn something or boil something. You may change the state of some kind of matter. You may change its chemical composition, but basically the same number of protons, neutrons, and electrons are still going to be there. And so the amount of matter in the universe essentially stays conserved. There's a law of conservation for charge, electrical charge, and we'll talk about that when we talk about electricity and magnetism. We're also going to talk about the law of conservation of energy when we get to chapter 7, which is also part of, that'll be our next chapter. And of course, there is a law of conservation for momentum. So what does it mean to say that momentum is conserved? Well, that means that unless there is an impulse on a system, that the momentum in that system must be conserved. And if we consider two colliding objects, they might collide inelastically, sticking together, like cars that deform as the result of a collision. Or they could be two objects that don't stick together and collide elastically, like a billiard ball bouncing off the bumper, right? Reversing its momentum. That means the total momentum of the system before and after the collision equals the total momentum after the collision, right? And so the total amount of momentum in the universe essentially stays the same. Another way of saying that is change in momentum equals 0, or because change in momentum is final momentum minus initial momentum. You could also say the final momentum equals the initial momentum, right? If you take final momentum minus initial momentum equals 0, we just add the initial momentum to the other side. We can very clearly see that, very straightforwardly, that they're equal. Now, in order to drive this home, let's run through a very famous thought experiment here. So let's say you have one train car with mass m, moving with velocity v. Okay? And then it's going to approach another train car also with mass m, and they're going to collide. And when they collide, they're going to hook together, and they're going to travel off together. Okay? So when they hook up together, they're going to move off with velocity v prime. How big is v prime? Well, we can use conservation of momentum to try to figure that out. Okay? If we say that our change momentum is equal to 0, that means our initial momentum, what's over here, has to equal our final momentum, what's over here. Okay, so for our initial momentum, this has a mass of m and a velocity v, right? So this one has momentum mv. This has mass m but velocity 0, right? So this has no momentum initially, it's not moving. Okay, what do we got now? We got mv prime plus mv prime, or 2mv prime. But 2mv prime equals mv, right? So 2mv prime is equal to mv. We've got a common thing on both sides of the equation. If we just divide both sides by m, we get 2v prime is equal to v. If we divide both sides by 2, we can see v prime is equal to our initial velocity divided by 2. Long story short, momentum has to be conserved when these two train cars collide and hook and move off together, right? That makes a lot of sense. Now, we've got one train car moving before they collide, and we've got two moving afterwards. We doubled the mass, right? And remember, momentum is mass times velocity. We doubled the mass, so for the momentum to stay the same, we have to cut the velocity in half. We have two train cars moving now, we only had one before. They're going to move off with half of the initial velocity of the one train car. Makes a lot of sense. Now the next part is important for the sake of understanding. What can we say about momentum in more than one direction? Well, momentum has to be conserved, right? Would vertical momentum affect horizontal momentum? Why would something falling suddenly move to the left or right? Doesn't make any sense, right? And so vertical momentum, horizontal momentum have to be conserved separately and independently of each other. Let's take another classic example. Let's say you've got two asteroids, right? Both of the same mass, let's say. They're going to collide elastically, not inelastically like the train cars. One is going to move off this way, and one is going to move off this way. Now, we'll call this V1 and this V2. This will be like V2x. This will be V1x. Actually, I'll do those in sidebars. So here's V1. V1 is going to have two components, V1x and V1y. V2 is also going to have an x component or horizontal component and a vertical component, right? Now, velocity v, let me just draw it a little longer just so it makes a little more sense. So before, if we look at just the x momentum, this mass is going to have some momentum this way, right? It's moving this way, so it's moving this way, and it's going to move horizontally and vertically, right? So that means, also this one is going to move horizontally and vertically, right? So before we have mv horizontally, right? That's our horizontal momentum. Afterwards we got mv1x, right? The horizontal piece, and mv2x, right? So the horizontal momentum of this one gets split in between the two asteroids after they bounce off of each other, and they're both going to move one this way, both with a horizontal component. But what about the vertical component? There is no vertical component here, right? And so if we want to talk about the vertical component, there's nothing. But here we have two, right? We got mv2, or sorry, v1y plus mv2y. That means that the vertical component of this asteroid's momentum is equal to the vertical component of that asteroid's momentum. And so these have to also be conserved, right? Long story short, independent axes or independent directions, things that are perpendicular from each other, must have independently conserved momentum. Interesting stuff, right? In any case, I hope you've enjoyed this video, and I'll see you again for Chapter 7.